Welcome to ELET B70 Mechanical Systems. This is your professor, Roy Allard. This lecture is on lubrication. This is based on Chapter 4 of your textbook. We're going to go more in depth into lubricants, lubricant principles, specifications, additives, industrial oil lubrication, viscosity classifications, and then lastly, grease lubrication. We've talked a little bit about lubrication in the pneumatic and fluid power lecture, and we talked about the properties. We'll be going more detail into this lecture. We've also talked a little bit about sliding and the weight or force that causes friction, and we will be talking about that more in the next lecture when we talk about bearings, both a plain sliding bearing and a rolling element bearing. So a lot of these lectures tie together and build on one another. Just want to make a note, portions of this are from maxtorque.com. So we have a different type of action here. We have the weight, then we have force that's moving this weight, and then it's on rollers. So the rolling friction is going to be much less than if we just put this weight on a flat surface. So we want to have a flat surface to another flat surface. The gravity produced by the weight gives much more friction. So rolling friction is much lower. One of the main reasons is, look at the contact. We have very little contact that is on this flat surface. Where here we have a lot of contact. So our surface to surface contact is much greater. Since rolling friction is low, then sliding friction has to be much higher than that. It's based on the coefficient of friction and a downward force on the top surface. Now, more than just rolling or sliding friction, there are other factors. Now note, these are not in a progressive order in easiest to hardest or least to most. I just want to make that clear. So surface finish is one of them. This has to do a little bit of it, okay? But you can see rolling versus sliding has a much higher effect on friction than surface finish. Rolling and sliding is a large difference. But surface finish definitely is going to cause friction. When we have a very smooth, highly polished surface, we're going to have less friction than a less highly polished machine surface. A little rougher, we're going to have a lot more friction. Now the load, which we can define as the amount of pressure pushing those surfaces together, the higher the load, the more friction we're going to have. So when a machine is lightly loaded, then the friction will be much less. As we start to increase the load on that machine, then it will definitely have more friction. The next item on the list is the speed or the rate of the relative motion. A high speed will cause a different amount of friction than low speed. And high speed usually generates more heat. And heat is actually a byproduct of friction. Then the lubricant. Lubricant will definitely determine the friction. If we have no lubricant, then we have metal to metal contact, and we're going to have a lot of friction. We're going to heat up those parts, and the machine is going to fail prematurely, much sooner than it should. And we'll talk about the fluid, the viscosity, and the additives. Now, temperature. Temperature is going to affect the condition of the surfaces, and it will affect the lubricating viscosity. So let's talk about viscosity and some of the things that we need to define with lubricants. We'll be talking about that in a few slides. But first, let's talk a little bit more about surface finish on the next slide. Even though the material may seem very smooth, when we look at it, we can see small bumps called asperities. Now here is a material before the break-in period. You can see it's really magnified, and we're showing all these asperities on here. And as the machine is moving the two parts, you can see this is moving back and forth, and we are going to wear the asperities off. So we would have this film lubrication, and pretty soon it would get really smooth. This is similar to any equipment or machine. When it's brand new, the tolerances are very tight. It hasn't been run very long. It may have been tested in a factory setting before it was delivered to the facility, but it won't have achieved a break-in period. So friction is going to be a lot greater before the break-in period is complete. After the break-in period, we'll have much less friction. This slide talks about boundary lubrication, and we'll be going deeper into the different types of film lubrication in additional slides. So the asperities reduce the space between those surfaces, leading to less than desirable lubrication, and we'll define boundary and other type of film lubrications. Next, let's get into the specifications of lubricants. Viscosity is the property of a liquid that causes it to resist flow. So if we have a higher viscosity, the harder it is for that liquid to flow out of the container and into a machine. For example, in normal car differentials, for say a 2000 pickup truck, we'll have a 90 weight gear oil. That is the viscosity. That's the Society of Automotive Engineer viscosity rating, 90. Now in our engine, we'll have a much lower viscosity, or even an automatic transmission. So different types of machines are going to take different types of viscosities based on the engineering and design of the particular machine. So sometimes we require a small amount of lubricant with a thicker viscosity to lubricate all of our wear parts. And then other times we need a lot thinner material. Generally, when the machine is operating at high speeds, we need a thinner viscosity than when it's running at low speeds. Temperature also has a factor as well. The next item is the viscosity index. So this is the amount of change that the lubricant is going to have as the temperature changes. So as temperature changes, viscosity will change. The higher the viscosity index, the less it will change as heated. If we have a low viscosity index, then as that lubricant gets hot, it's going to get a lot thinner. The next thing is a pour point. This is the lowest temperature at which the lubricant will flow out of the container. So when it's colder than the pour point, it won't flow. So we have to be aware of the environment where we're going to use the lubricant. If we're up in Barrow, Alaska, where we're below zero 10 months out of the year, we definitely need to have a lubricant with a lower pour point. And a lot of times the temperature is several tens of degrees below zero. Where in California, and particularly Bakersfield, we may only get below zero hardly any time. We might get in the teens, but we're not going to see below zero temperatures down here in the valley. Now, we'll see below zeros up in the mountains at 8,000 and 10,000 feet in the Sierra Nevadas. So if we're using lubricant up there, we'd need to make sure the pour point was lower than 0 degrees. So that's what the pour point is. The next two definitions have to deal with flame and fire. Flash point is a temperature at which the lubricant vaporizes enough where it can be ignited, but it's not going to sustain a flame and a burning action. It's just going to flash into a flame and then extinguish itself. Then the fire point is going to be a higher temperature at which the lubricant will vaporize enough to support a continuous flame. So we need to be aware of these specifications and make sure if it's being used in a machine that's going to generate an extreme amount of heat, that the machine is not going to catch on fire. So fire point and flash point, two very important specifications of lubricant. Next, we're going to talk about lubricant additives. The first item is a viscosity modifier. So these are polymers that are added to the lubricant, generally oil, to increase the viscosity at higher temperatures. They increase the temperature range over which that lubricant can be used. So as the lubricant gets hot, the lubricant generally gets thinner. If it gets too thin to accurately or completely lubricate to keep the metal parts from touching, then we're going to have high friction and high wear. So we need to maintain that viscosity, and if we do at a high temperature, the viscosity modifiers help us do that. Another modifier or additive, an additive is detergent. They prevent contaminants from accumulating on component surfaces. So we think of a detergent that we can clean the machine, but it just prevents contamination accumulating on the machine. It also will neutralize the effects of product combustion or oxidation. So when we have air, and air is in this machine with this lubricant, oxidation will occur because of the oxygen in the air. It also helps parts be protected against varnish and carbon buildups. So almost all lubricants have some form of detergents to help combat these problems. An important additive is a dispersant. It minimizes the ability of those contaminants, the dirt, the grime, the metal particles, to form these large lumps that settle as varnish or sludge. So it actually keeps them small and separated, distributed throughout the lubricant oil, so they don't block or clog any ports that the machine uses to distribute the lubricant in that machine. Now, at a point, all lubricant is going to wear out, and that's why we need to change it. Other additives are anti-wear agents and extreme pressure agents. They help reduce the loss of metal from those component surfaces by preventing the metal-to-metal contact under high load. So there's an extreme pressure agent that I have to put in my vehicle's differential, and it's added to the lubricant itself. So it's a separate bottle. Antioxidants. So petroleum-based lubricants are made from hydrocarbons, which is part hydrogen and part oxygen molecules that are linked tightly together. As those lubricants are exposed to air and the heat, they're going to absorb oxygen from the surrounding air, and it creates a chemical change in that lubricant that can cause many problems, breaking the lubricant down. So antioxidants are used to help slow the oxidation process. Next, there's rust and corrosion inhibitors. It improves the lubricant's ability to stick to metal surfaces. Because if we have a lubricant on metal, then oxygen can't get to it and moisture can't get to it, the moisture from water molecules, so then the metal is unable to rust. Next, there's anti-foam additives. So they actually inhibit foam from being created out of the lubricant. So it prevents the oil from trapping that air and turning into foam, because foam is not a proper lubricant. Just think when you're washing dishes and you put some soap in the sink, you plug the drain and you add water to it. Well, the suds will come up to the top. But if you get that and take a handful of suds, there's not much to it. That would be the same as foam in lubricant. It wouldn't properly coat the metal and lubricate the machine. We're going to look at different lubrication comparisons. Now remember, what we're trying to do with lubricant is completely stop the metal-to-metal contact. So we want the metal to be coated with a film of lubricant so the metal isn't in contact with other metal. So we'll just have no lubrication, as in this top one. And we'll have dry surfaces in contact with the other dry surfaces on both sides. When we have a full film lubrication, we have an oil film completely separating the two different surfaces. So here's the gray is the surfaces and the yellow is the lubricant, and nowhere along this yellow area do we have the metal-to-metal contact. So we've achieved that. And here we have metal-to-metal contact with no oil or no lubrication. So this is considered a full film lubrication. Then we have a mixed film lubrication where we have oil and boundary film, and they kind of play a role. So right here we're kind of getting close to boundary. We're not full film, but we're not a full boundary film, and so we have what we call mixed film lubrication. And then in boundary film, it's the performance is completely dependent on boundary film, and the additives create a boundary film that protects the metal surfaces. So remember those additives that cause the oil to adhere to the metal surfaces and to disperse any granular parts of metal and dirt and grime and things like that. So you can see this boundary film in blue on all of these. So let's take a little closer look on the next slide. So we have the same image with these 4 levels of lubrication: no, full film, mixed film, and boundary. So what is determining these is the thickness of the film of the lubrication on the metal parts. So full film, where we have full film lubrication right here, we call it hydrodynamic. So the lubrication surfaces are fully separated by a fluid film. Elastohydrodynamic is a mixed film. So the two surfaces are separated by a very thin fluid film. So it's kind of between the mixed and the full. So we're not going to have this touching spot area. So a little bit in between these two. And then the mixed film, where we have partially separated and partially in contact, like down here. And then the boundary lubrication, the two surfaces are mostly in contact with each other, but we have a thin fluid film present. So we consider full, mixed, boundary, and then of course no lubrication. No lubrication would be a detriment to our equipment. We'd have extreme heat, extreme wear loss, lots of friction, and metal-to-metal contact, which is what we're trying to avoid with a lubricant. There are three main types of oil or lubrication that we use in industry. Animal and vegetable oils, so they're made from animal fats or oils from vegetables and plants. Mineral oils, which are petroleum-based oils, so they're distilled from crude oil that comes up out of the ground. We're famous in the Kern River and Kern County, in the West Valley, the Midway Sunset, Taft, Maricopa area for our petroleum-based crude that comes out of the ground. And then there's synthetic oils, the third type. So they consist of a chemically made compound that are artificial. So we call it synthetic. They're artificially made using petroleum components that are chemically modified. So we don't use the whole crude oil, but we do use a component of petroleum. They can also be synthesized from other raw materials. So synthetic oils. Some of you may be thinking, why would we use vegetable oil for lubricant? Well, it depends on the manufacturing process. If we have a conveyor system and operating machinery and we're making food grade products, then we need to use a food grade lubricant. We wouldn't want a petroleum based oil distilled from crude to get a little splash into our food that is being made on this assembly line. That would be contamination. So if we're using a vegetable oil is 100% edible, non-toxic in any way, and that would allow it to be used in a food assembly manufacturing area. Now let's take a look at the difference between synthetic and conventional oil. So we already said that the synthetic oils are made from components of petroleum or from other materials, and they perform better because of a more uniform molecule size. So you can see the molecule size is more uniform. Now this obviously is microscopic, what we're looking at. We don't dump big balls of oil out of an oil container. But when we enlarge this, we see the molecules, and they're a more uniform size with synthetic oil. More uniform, less friction. We're going to have more friction and different sizes of molecules. Now, there's been a lot of studies done, and for the most part, whether you use synthetic or conventional oil in an automobile, and they are fully compatible with each other. If we had a 5-weight 30 conventional oil in, and we were running a quart low on oil, and all we had lying around or in the store was a 5-weight 30 synthetic, we could simply add it to the conventional oil. We can mix these two. Now, we wouldn't want to mix it in an oil change, but we could. It is fully compatible. What you're going to get with synthetic oil is a longer lasting oil, because we're not breaking down the oil as fast because the molecules are the same size. Here we're going to break down these larger molecules, and the oil is going to break down. So then it's going to have less of an ability to coat the metal products properly. And the oil is going to get dirtier faster and will need to be replaced sooner. So for the most part, synthetic versus conventional is about the same cost, because with conventional it's cheaper, sure, but we have to replace the oil sooner on a more periodic basis. Where synthetic will last longer, a lot of times over twice as long. So depending on that and the price of the synthetic versus the conventional, you may save a little money with synthetic. But it's more expensive, you don't have to change it as much, so they're pretty close in cost. So what do you want to run? Well, if you can afford and want to do fewer oil changes, then I'd probably go with synthetic oil. But there is really no hard, fast difference in costs. But there is one thing that you want to follow. If your manufacturer's manual, your owner's manual for your automobile or the equipment that you're maintaining states using synthetic or a full synthetic oil, then by golly, you should probably do that. Even though Society of Automotive Engineers for vehicles says that these two will mix just fine and you can use either one. So definitely side with the manufacturer on this, and that's what I would do. And some automobiles recommend only synthetic oil in their engines and gearboxes and things like that. So definitely look at the owner's manual. And in industry, we'd want to do the same thing, right? The equipment's designed to operate under certain conditions with certain parts. And we want to make sure that we're doing that unless there is a change or a bulletin from the manufacturer of our automation equipment that says we can do something different. So you'll always want to use what's recommended. Next, we're going to talk about viscosity classifications. So this is just what you're thinking, like a 90 weight gear oil versus a 10 weight motor oil or transmission fluid versus a 40 or 50 weight oil. The higher the viscosity number, the thicker the oil is. We talked about that early on in the lecture here. So in the US, it's determined by a viscometer. So it's measuring viscosity. So simply, the lubricant's placed in a container, and then the container is heated and maintained at a certain temperature, and then we allow the fluid to flow out, the lubricant, and it's timed. So it fills a flask, and the flask is called a Saybolt flask. And the number of seconds that it takes to fill up this container is the amount of Saybolt universal seconds. So the viscosity is then determined by the SUS value. So simply said, if it takes longer to flow out, it's going to have a higher viscosity, or longer to fill this predetermined amount in this flask. The quicker it fills it, it's going to have a lower viscosity, and that's how it's determined. The image on the bottom is an actual viscometer that is measuring the viscosity of lubricant. So if we were in the rest of the world, it might be using the newer system, the ISO 3448. So it uses something called centistokes rather than the Saybolt universal number, and the Celsius temperature scale as opposed to Fahrenheit. So lubricants at certain temperature are allowed to flow through, again, small capillary tubes, and the flow is timed. So it's very similar in nature, but we have what we call an ISO VG grade versus to an SAE crankcase oil grade that we're familiar with in the United States. Generally, a machine that is made in France or in Europe, such as a bottling machine that requires lubricant, the manual is going to have it in both the ISO VG number and the SAE number. But if you don't have it in both, you might have a manual that may only have it in one or the other, then definitely you can use a conversion chart to look it up. Now there's also graphs like this one on this slide that show the viscosity versus temperature curves of different materials. Now this is hard to read, but you can see ethylene oxide, benzene, diesel fuel, fuel oil. Here is silicone fluid with the specification number after it. SAE oil and whatnot. And this is the viscosity, the kinematic viscosity in centistokes, and this is the temperature in Fahrenheit. So you can see as the material, such as diesel fuel here, this one's kind of on its own, as the temperature is warmer, the viscosity decreases. So the material gets thinner. And that's generally similar with almost everything on this chart. I shouldn't even say almost. Everything goes from the top left down to the bottom right at some angle of line. So everything is getting thinner as it heats up, or a lower viscosity. In the lubrication chapter 4 inside your textbook, it contains some additional details about the American Petroleum Institute service ratings and standards for engine oils and gear lubricants. So you'll want to look at this to understand what's involved. But the API ratings, the American Petroleum Institute ratings, are not going to be included on the midterm that's coming up. So now let's talk about grease. No, not the movie with John Travolta, but the lubricant grease. Grease accounts for approximately 10% of the total lubricant used in the world. The rest would be mineral oil, which is petroleum-based, animal or vegetable oils, or the synthetic oils. So 90% is oil of some type, and 10% is grease. Now, oil is better than grease because it can produce a very uniform film across and coating all of the metal surfaces. It is thinner, so it generates less friction. And it's also a better coolant than grease. But grease does have advantages. And you'll need to remember this slide and these advantages on the upcoming midterm and the final, because we need to understand why grease is used. And these 4 bullet points state it very clearly. So they're not in any particular order, but we'll go from top to bottom. Bearings can be sealed, holding the lubrication in and contaminants out. So we can have a sealed, encased bearing with the grease pre-installed. Grease will stay in place where oil would simply run out. So if we're trying to do some lubricant, we can coat the metal surfaces or whatever we're lubricating with a thick grease, and it's going to stay in place. It's not going to drip off. It's not going to run to the bottom. Third, grease generally withstands much higher temperatures. And one of the important factors, it decreases the frequency of lubrication maintenance. So let's talk about your wheel bearings in an automobile. Those bearings, those tapered roller bearings, we'll be talking about those next week, by the way. Those tapered roller bearings are actually filled or packed with a grease. Now, that will last much, much longer than the oil in our engine or the transmission fluid in our transmission. So decreases the frequency of the maintenance. Now, there's some other factors that are involved that we could talk about. The engine is running at a higher operating temperature and a faster RPM than your wheels are spinning. I guess it depends how fast you're driving, but they will last much longer on a case-to-case basis with oil and grease. So you'll want to make sure that you take notes on these 4 advantages of grease. Even though oil is considered to be a better lubricant, grease has these 4 advantages. When we look at the content of grease, It's made up of a petroleum-based oil and a thickening agent, so it's thick oil. That's what grease is. And a thickening agent is called soap. And then it'll have some other additives to enhance its lubrication properties. So when we look at the amount of oil in grease, it's approximately 80 to 90% based on the type of grease. Then the next greatest quantity in grease is the soap. So the soap's added to hold the oil where it is placed inside a bearing, on a metal surface, and then releases the oil slowly. So it's thick oil. By volume, additives are next, and they make up a very small amount. And here you can see 4 different types, maybe 3. This looks very similar to this picture, different types and different colors. So what makes the grease different is the type of soap that's being used to thicken it. And we'll look at that on the next few slides. The first type of grease is called calcium soap grease because it's using calcium as a soap. It can also be called lime soap. It's the first grease type that was used. It's inexpensive. It contains 1 to 3% water to help combine the soap. It's a low temperature grease, so it can't be used over 180 degrees of temperature. And this is in Fahrenheit. So it's generally used for low speed, low temperature applications, and it works well in wet environments. So it's important if it's a grease that can't be broken down with water. And here's some examples that can come in some different colors. The next type is sodium soap grease. So it's a low cost, because sodium is pretty plentiful, general purpose grease. Wow, look at 250 degrees. So that's 70 degrees higher than the calcium or lime grease. It has a fibrous texture when you feel it in between your fingers. It's often used for bearings, and it should only be used for slow speed applications. Now this grease is water soluble, and it holds water, so it should only be used in dry environments. So we wouldn't want to use a sodium grease on a wheel bearing for a boat trailer, especially when that boat trailer has to be put in the water when we're launching a boat off the trailer. So that would be a big no-no, because as the wheels are under the water, the wheels that are on the trailer, that grease is going to get washed out of those bearings. Now, you could back it in one time quickly, launch your boat and come out, and you're going to have grease in there. It's not just going to come pouring out, but over time and swishing in and out of that boat ramp, you're going to run all that grease out of your bearings. And when you do, what are we going to have that we're trying to prevent with lubrication? Metal to metal contact. Those bearings will wear prematurely and fail, and could actually heat up enough to fuse to the spindle and actually heat that spindle to where it just falls off the trailer. I've actually seen trailers on the side of the highway where the axle is actually broken off and the bearing race is actually fused to the axle because it overheated due to the lack of lubricant. So you want to make sure that you're using a lubricant for the intended application, and you wouldn't want to use this sodium grease for wheel bearings for a boat trailer because we put boats in water. The next type of grease is lithium soap grease. It's probably the best general purpose grease. Sometimes we even call it multi-purpose because we can use it for different things. It's good for higher temperatures. Wow, we went up another 50 degrees from 250 for the sodium, up to 300 degrees for the lithium. With the proper additives, it's good for cold weather environments, and it has really good water resistant properties. I actually use a synthetic lithium soap grease on my snowmobile chassis. So we have the slide rail suspension on the back that the track is rotating around. And there are some pivot points where it pivots when you're going up and over or jumping or just moving. The track is constantly moving up and down because the snow path, just like a road, isn't totally 100% smooth. So we're having some slight movement in some of the chassis joints. And so those have to be lubricated because we want to prevent that metal on metal contact, because over time we'll just wear right through the metal. So the grease is pushed in there and it is keeping it from having that metal contact. And so we use lithium and an actual synthetic, which we'll be talking about in the next couple of slides, which has really good water resistant properties. So I wouldn't want to use a sodium type of grease, because what is snow? Well, snow is a little more solid form of water, but that snow's going to melt and that would wash the grease out. So need to use a grease for the intended purpose, whether the location is wet or dry. That's very important. And it's good for higher temperatures. Next is called a complex soap grease. So instead of the conventional soaps like lithium or calcium or lime, they actually use a metallic thickener. They're used specifically for high temp applications. They aren't as effective with other greases with those additives, but it's usually much more expensive and it works for high temperatures. So depending on the operating temperature, we need to get the proper grease. Again, just like oil lubricant, grease is a lubricant as well, and we would want to follow the manufacturer's guidelines or specifications for the correct type of grease that we're going to use on this machine. This last slide is on synthetic grease. It's superior, more expensive, but it has a high heat resistance, low oxidation when it's exposed to the air, and it's highly efficient. And there are 4 types of synthetic grease. They are organic esters, so that has a wide temperature range, polyglycols, high temperature but very low water resistance, silicone synthetic grease, very high cost but also high temperature and good water resistant. And then synthetic hydrocarbons, so not quite as good as the others, but better than the standard non-synthetic petroleum-based greases. So I can't stress this enough. One more time, for lubricant oil and lubricant grease, you want to go with what the manufacturer is recommending to use in the machine or the apparatus that you're actually lubricating. We're done with lubrication and chapter 4, and I hope you enjoyed this lecture. If you have any questions after watching this video and reading the textbook, please post them in the Q&A discussion. Thank you very much for watching.